Welcome to today's Explainer. We're going to track one of the coolest journeys in our solar system, the path of a single, solitary sunbeam. We're going to break down exactly how solar energy travels, how it interacts with our planet, and how it ultimately acts as the grand engine driving literally all of our weather. So let's just dive right in. Have you ever wondered what our planet would feel like if we completely stripped away our atmosphere? Well, it would be a freezing -18 degrees Celsius. Yeah, really cold. But instead, our global average sits at a super comfortable, life-sustaining positive 15 degrees. That is a massive 33-degree difference. Life as we know it absolutely depends on this precise warming effect. And getting a handle on exactly how we get those 33 degrees, that's the whole key to understanding our entire climate system. Section 1. Earth's solar engine. Okay, so the sun is the ultimate source of power for our weather. Every single second, it is blasting a truly enormous amount of electromagnetic energy out into the freezing void of space. A tiny, tiny fraction of that energy actually reaches Earth, coming in across various spectrums like visible light, ultraviolet, and infrared radiation. But what happens the very second that energy arrives? Well, the sunlight basically splits into three pathways. Exactly 30% of that incoming solar energy gets immediately reflected right back into space by things like clouds, ice, and bright surfaces. Then 20% gets absorbed by the atmosphere itself as the light passes through. And that leaves the largest chunk, 50%, which makes it all the way down and gets absorbed by Earth's surface. Let's zoom in on that 30% that gets bounced straight back into space. This brings up a really crucial concept called albedo. Albedo is simply the fraction of incoming solar radiation that gets reflected by a surface. Basically, it determines if a surface acts more like a mirror or more like a sponge. Light-colored surfaces, like snow, ice, or those really thick clouds, have a very high albedo. They're the mirrors. They reflect a ton of energy. Dark surfaces, on the other hand, like dense forests or deep oceans, have a low albedo, meaning they act like sponges and soak up way more of that energy. The extreme contrast we have on our planet's surface is honestly incredible. Take fresh snow, for example. It has an albedo of about 0.80 to 0.90, meaning it reflects between 80 and 90% of the sunlight that hits it. It is literally a giant natural mirror. But then look at the open ocean. It has an albedo of just 0.06, so it absorbs a whopping 94% of the sunlight that strikes it. Now, the really critical part is understanding what happens when those two totally different surfaces interact. When sea ice melts, it replaces a highly reflective, mirror-like surface with dark, heat-absorbing ocean water. And because that dark water absorbs more solar energy, it naturally warms up even further, which, you guessed it, melts even more ice. Scientists call this a positive feedback loop. It's a cycle where the effect actually reinforces its own cause, speeding up the overall warming process. It's a huge reason why scientists monitor polar ice melt so incredibly closely today. Section 2. The natural greenhouse effect. So what about that 50% of energy that was absorbed by the Earth's surface? Well, the surface warms up, but it doesn't just hold on to that heat forever. It actually re-emits it. But it doesn't send it back as visible light. It radiates invisible thermal energy, which we call infrared radiation. Here's exactly how that creates our life-saving 33-degree warming effect step by step. First, sunlight passes right through the atmosphere and warms the Earth's surface. Second, that warmed surface emits thermal energy, infrared radiation, back up toward space. Third, greenhouse gases hanging out in our atmosphere, like water vapor, carbon dioxide, methane, and nitrous oxide, intercept and absorb some of that outgoing infrared. And finally, step 4, those gas molecules re-emit the absorbed energy in all directions, including right back down to Earth. This return radiation is exactly what warms the lower atmosphere and the surface, giving us the habitable climate we know and love. Now, a quick aside on the name itself. We call it the greenhouse effect because, well, it's a really handy analogy. But it's actually important to know that the physics are a bit different. A literal glass greenhouse stays warm mostly by physically blocking warm air from rising and escaping. It prevents what we call convection. Our atmosphere, on the other hand, traps heat through the absorption and re-emission of radiation. So while the overall warming effect is super similar, the actual physical mechanism going on up there is quite different. To truly appreciate our atmosphere, we really just need to look at our planetary neighbors. Venus has a phenomenally thick atmosphere made of 96% carbon dioxide. Its extreme greenhouse effect drives surface temperatures to a literally lead-melting 465 degrees Celsius. Mars, on the flip side, has a super thin atmosphere with almost zero greenhouse warming, leaving it sitting at a bitter -60 degrees. Earth? We have a moderate greenhouse effect. It gives us our perfect Goldilocks average of 15 degrees. Not too hot, not too cold, just right. Section 3. How heat moves. So we know how heat gets trapped, but how exactly does it move around our planet to actually drive our daily weather? Energy moves through 3 specific mechanisms. The first is radiation. This is the transfer of energy through electromagnetic waves. And what makes radiation so incredibly special is that it requires absolutely no medium to travel through. It is the only way the sun's massive energy can cross millions of miles of completely empty vacuum space to reach us. All objects emit some form of radiation, and the warmer the object, the more it emits. So the sun radiates visible light to us, and the Earth radiates infrared energy back. The second mechanism is conduction. You can think of this as the transfer of thermal energy through direct, physical contact between molecules. The energy just passes right from one molecule to the next. If you've ever stood barefoot on sun-baked pavement on a hot summer day, you've definitely experienced this. The hot ground directly heats the extremely thin layer of air immediately touching it. But here's the thing. Air itself is actually a pretty terrible conductor, so this method alone is absolutely not enough to heat our entire atmosphere. And that brings us to our third and arguably most dynamic mechanism, convection. This is the transfer of thermal energy by the actual physical movement of a fluid. And remember, in physics, gases like our atmosphere count as fluids. When that thin layer of air right near the ground gets heated by conduction, it expands and becomes less dense. Because it's lighter, it rises upward. Then, cooler, denser air from above sinks down to replace it. This creates a continuous, rolling loop that we call a convection current. Convection is absolutely the undisputed heavyweight champion of heat transfer in our atmosphere. Those rising and sinking air currents aren't just invisible pockets of temperature, they are the fundamental drivers of our entire weather system. As warm, moist air rises via convection, it cools and causes cloud formation. And on a massive scale, these huge convection currents act as the engine that powers the great wind belts encircling our whole globe. Section 4. The global energy budget. To tie all of this together, we really have to look at the big picture. Just like your personal finances, the Earth operates on a very strict budget. We have incoming deposits from the sun and outgoing expenses radiating back into space. For our climate to stay stable, the system has to achieve what we call radiative balance. That's where the outgoing energy precisely matches the incoming energy over time. It's a perfect equilibrium. Remember how we said 30% of the sun's energy is immediately reflected? That leaves exactly 70% that is absorbed, 20 by the atmosphere, 50 by the surface. Well, to maintain our radiative balance and keep the planet from endlessly heating up or cooling down, the Earth and its atmosphere have to eventually radiate exactly 70% of that energy back out into deep space as infrared radiation. Deposits equal expenses. Simple as that. But what happens if we start altering the variables in that budget? Well, this is where the enhanced greenhouse effect comes into play. If we add additional greenhouse gases to our atmosphere, they act like a much thicker blanket. They trap more of that outgoing infrared radiation than they used to. This temporarily shifts our really delicate global budget out of balance. It results in a warming trend because the planet is suddenly holding on to more heat than it's immediately releasing back to space. And that brings us to the ultimate question I want to leave you with today. We've seen just how perfectly balanced our planetary engine naturally is. But what happens to our global energy budget if our planetary albedo drops because of melting ice, severely cutting down our reflected energy? Or what if the concentration of heat-trapping greenhouse gases just continues to increase? Both of these powerful scenarios shift our radiative balance directly toward warming. It is a completely fascinating yet deeply fragile system, and understanding this basic energy math is the very foundation of all climate science. Thank you so much for joining me on today's Explainer, and keep learning.